So using graphs to solve inequalities. I'll start off with the good old classic, pro-numeral and denominator question. Now, I'm not suggesting that this is the best way of solving this sort of inequality, but of course you could. If I was to draw x squared divided by x plus 2, so what does that look like? Well, let's construct it. I've drawn y equals x squared and also the line x plus 2. I'm dividing the parabola by the line. Okay, that means I've got a vertical asymptote at -2. Working out the areas that I'm in, because we end up with, let's just go through it, we would have a positive divided by a negative, so it's negative. Positive divided by a positive, it's positive. Positive divided by positive, and the rest is positive. So let's work out the asymptote. So working out the oblique asymptote, it's going to be x minus 2. Draw that in. Okay, I've got to bend towards the asymptote. I've got to stay in the shaded areas. So that would be the graph there. Our question now is, when is that graph that I've just drawn in below y equals 1? So the red line. Of course, using this technique relies on an accurate graph. Now, I got lucky here because they turned out to be nice, neat integers and it's fallen right on the intersection. But if it's not, then it becomes really hard to use a graph to do this. But I can read off this one. But if I couldn't read off it, I suppose I could solve the equation and go, oh, it must be x equals 2 and minus 1, those 2 points of intersection. I want below the line, so there's my solution. X is less than minus 2, or x is in between minus 1 and 2, and including those points. As I say, not the greatest way to solve that sort of question, but you could use a graph to solve that type of inequality. Let's look at more interesting ones. Whoa, that is getting old, this question. 1990. Okay, this comes from the 1990 HSC. They gave us the square root graph and they've labelled particular points there. First part simply said, well, show that this graph is increasing. Well, you just gave me a picture. I can see, look, it's going up, it's increased. But anyway, they want us to show that it is. So how did I do it? So, well, I know a curve's increasing when the derivative is positive. The derivative of root x is 1 on 2 root x, and that's certainly always positive. So I know that it's always positive for x is greater than 0. The next bit, did I have to worry about it? I said, well, that's greater than 0. They said, show it's increasing for greater than or equal to 0. But if 0 is the starting point, can you really say it's increasing at that point, because that's when it starts from? That's what I mean. Do I really need to worry about x equals 0 or not? But anyway, I did. At x equals 0, y equals 0. And when x is greater than 0, y is greater than 0, so it must have increased from that point. Maybe overkill. Therefore, the curve is increasing for x is greater than or equal to 0. Hence, go and show this wonderful expression. And that's where the graph comes in handy, and they're sort of highlighting this. We're going to use the idea that the outer rectangles here, the area of those outer rectangles, is clearly got to be greater than the area under the curve. So it's a hidden hint. By giving us a diagram, though, hopefully people pick up on it and go, oh yeah, that's the idea we're using here. Okay, we know it's increasing, so the area of our outer rectangles will be greater than or equal to the area under the curve. Well, the area of each of those rectangles, we can see the width of each of them is 1. There's going to be the y values, the square root of 1, the square root of 2, so on up to the square root of n, which will be greater than or equal to, theoretically equal to, the integral from 0 to n. So we've done half of it, but now basically they're saying, oh, can you go and work out this integral, please? So we integrate root x, we get 2/3 x root x, sub in n, sub in 0. We've got the answer. Okay, so we've done that part. Use induction to show that it's less than or equal to 4n plus 3 on 6 root n. So the first part in B here, we've shown that that sum is greater than a certain amount. Now we're going to use induction to show that it's less than a certain amount. So it's one of our inequality inductions. Okay, prove it true for the first case. Left hand side is the square root of 1, which is 1. Right hand side we get 7/6. Yep, it's certainly less than or equal to. In this case it's less than, but that does mean it's less than or equal to. So true for 1. We will assume what it is that they're asking us to prove. And we want to then go and prove the next case. So this is what I'm going to try and prove. Again, I'm using the technique of let's move everything to one side. I'm going to show it's always less than or equal to 0. It's a series type, so I'll do it that way so I can get my assumption substituted in, and I end up with less than or equal to 4k plus 3 on 6 root k minus 4k plus 1 on 6 root k plus 1. What am I heading to? That's right, I want to show it's less than or equal to 0, don't I? Oh, nicely, oh, I was going to say those fractions are the same. They're not quite the same. Denominator is the same, which makes life a little bit easier. I want to try and subtract here. I'm going to make the first one a complete surd, so I can subtract the surds, because I need that irrational part, that surd, to be the same. So if I throw that 4k plus 3 inside the surd, it becomes 4k plus 3 squared. 16k cubed plus 24k squared plus 9k. I want k plus 1. How do I do it? Well, I'll divide by k plus 1. It doesn't go in exactly. I've got a remainder of -1, but that's okay because I'm dealing with inequality, not equality. So now I can say, oh, well, that has got to be less than that. Because clearly, if I subtract 1, I must have a smaller number than the next line. See? Beautiful. That's the beauty of inequalities rather than equalities. That -1, not a problem. Yeah, get rid of it. Because I still have a true statement. But now, look at what I got. I got that k plus 1 I'm looking for, and look in the second one. That's a perfect square. Not just any perfect square, by the way. It's 4k plus 1 squared. Pull it out. Oh, that's 0. And that was what I want to try and prove. So hence, it's true for k plus 1 if it is true for k. And then we can induce that it's true all the time. Okay. Use B and C to estimate the value of the square root of 1 plus the square root of 2 all the way up to the square root of 10,000. Now I suppose if you're incredibly patient, you could put that into your calculator. We have basically now sandwiched this square root of 1 up to the square root of n in between these two expressions. We want the one where n is 10,000. So let's substitute in 10,000. What does the left-hand side become? Wow, to the nearest 100, the left-hand side is 666,700. So is the right-hand side. Well, if it's in between them, there's only one possibility. It is that. So 666,700. Now, if you want to check, of course, pull your calculator out, get square root of 1 plus square root of 2. No, I wouldn't do it that way. I'd set up a spreadsheet. It's going to be easier. Write a formula, square root of this, fill down, sum. That would be the smarter way of doing it. Don't use your calculator. It'll take you ages. Let's prove this one. Okay. We'll prove it using a graph. There's y equals x, and I'll draw in y equals sine x. Now again, it's not good enough for a proof to say, oh, look at that, the line's always above the curve, you little beauty. We've got to prove it. So let's find some values. Well, function x is x, so the derivative is 1. I know the slope of that line is always 1. Okay. Now let's look at sine x. The derivative of sine x, it's cos x. Well, between 0 and pi on 2, so I'm just interested in that section there, I know that cos x is always less than 1. So what that's telling me is the slope of the curve is always less than the slope of the line, i.e. the line is rising quicker than the curve. Now, if they start at the same point and the line is rising quicker, then the line has always got to be above the curve. It stops at 1. We know that its range is in between -1 and 1. Y equals x keeps going. So it's not a problem. We know x is greater than sine x after that point. So therefore it's always, x is always greater than sine x when x is a positive number. 2f.